So now we're going to talk about a required practical, and it's to investigate how the rate of the reaction of sodium thiosulfate with hydrochloric acid changes as the temperature of the reaction is changed. And so here we have the chemical equation, and what you can see is that sulfur is produced, and sulfur is a precipitate. So that means that the original colourless solution of the hydrochloric acid and sodium thiosulfate will not be colourless anymore because it'll have a precipitate, so it'll be kind of cloudy. And so the rate of this reaction can be measured by measuring the time taken for a fixed amount of sulfur to be produced. So an easy method to do this would be using a cross underneath the conical flask, and you can time how long it takes for the cross to disappear as it's obscured by the sulfur precipitate. So what we do is we first use a 50 centimeters cubed measuring cylinder to add about 50 centimeters cubed of sodium thiosulfate solution to a conical flask, and we carefully record the temperature of the solution. Then we place this flask onto the piece of card with the cross on it, and then we add 10 centimeters cubed of hydrochloric acid to a test tube using a measuring cylinder again, and place it into a test tube rack. When we're ready, we then add the 10 centimeters cubed of hydrochloric acid to the sodium thiosulfate. We quickly give the contents of the flask a swirl, and then look down through the side of the conical flask to time how long it takes for the cross to disappear. We then take the final temperature of the solution and then record this together with the time taken for the cross to disappear using a results table. So what we do is basically we measure the temperature before and the temperature after, so we can get a mean temperature, and then we can work out the rate by dividing 1 over the time. And so we get a graph eventually that looks like the one on the right, where we can compare different temperatures. And the way we can measure other temperatures is either by using by putting the conical flask into an ice bath for colder temperatures, or heating them up using a Bunsen for the higher temperatures. And so we get a graph that looks like the one on the right, and then we can compare the rate depending on the temperature. So we can see that as the temperature increases, this makes sense because when we increase the temperature of something, we give the particles more kinetic energy. So there are more collisions per unit time, and also more of the particles then possess the activation energy required for a successful collision. So overall, there are more successful collisions per unit time, and so the rate of reaction increases.